Hey guys, welcome to your, I guess this is your technically your second lecture of the semester. Exciting, right? It's very exciting. I really wish that I could be face to face with you guys and get to see all of your beautiful faces every day in person, but we're just going to get through it. We're going to do this. So here we go. Second lecture, 2.2, the limit of a function. In this lecture, we're going to talk about limit notation. How do you write these things? Finding a limit numerically, right and left hand limits, and infinite limits. And of course, we're going to discuss what even the heck a limit is, right? Before we get into that, let's just talk about limit notation. How do we write these things? Okay, so limit notation, we have it right here. If you guys follow my red pen, let's talk about this. It says lim, then f of x, and on the bottom here I have x arrow a, right? What does that mean? Well, the way that you pronounce that is the limit of f of x as x approaches a. Okay, this first bulletin here, we have some more notation. It says limit of f of x as x approaches a is equal to L. What that means is that as my x values get really, really close to a, but not equal to it, the corresponding y values get really close to L. Now I know it's kind of weird, but let's go ahead and take a look at a graph, and we're going to try to put into play what exactly is even going on here. So if you take a look at this right here, I have a down here, that's my x value, then I appear to have some L value here. Now, let's say we do not know what L is. We do not know what the y value is. That's why up there it says expected y value, question mark, because we don't know what it is. So what a limit is really doing is we're saying, okay, you know what? If I don't know what the y value is at some specific x value, what we can do is we can look at what happens when I get really close to a from the left or from the right. What happens when I choose x values that maybe are a little bit greater or a little bit less than a? What happens if I look at those x values and I look at the y values that pertain to them? Where do they seem to be going? So for instance, let's do this in purple. Let's say I chose an x value here. It's not super close to a, but it's on the left-hand side of a. And then I figured out where it hits the graph, and then I figured out the y value that pertains to it being right here, right? And then I said, okay, let me choose another point that's a little bit closer to a, still on the left-hand side. And then I figured out where that hits my graph, and then draw a horizontal line over to the y-axis. Okay, that's right there. Can you guys see that as I'm getting closer to a, my y values are getting closer to that L? It's getting closer to whatever y value L is. And if I do the same thing on the right-hand side of a, so maybe I pick something right here, and I see where it hits the graph, and then I connect it over to the y-axis and say, okay, it's right here. There's my y value. And I do one more, even closer to a, but still on the right-hand side of it, and see where it touches the graph, connect it over to the vertical axis, the y-axis. And you guys can see, okay, as I'm getting closer to a from the right and from the left, as my x values are getting closer, my y values are getting closer to L. So this is the idea. Now, we may not know what L is. L might be something that we can't figure out. But what we can do is we can take a limit as x approaches the value in question to try and figure out what the y value is, what's the outcome. So that's kind of the idea of a limit. And it's going to make a little bit more sense. I know we just had a lecture on average velocity and instantaneous velocity, and now we're talking about limits, and it's like, what the heck is going on? Why are we doing this? Calculus is taught in stages, and we kind of have to get the background pieces set up so that we can start to get into a little bit more of the fun stuff where everything comes together. and it will come together, I promise. But for now, we're going to keep talking about these limits and how to evaluate them. So back to our limit notation, we're going to move away from the graph for a second. So let's say we had to do this problem. So read it with me. It says example 2.20, find the limit of x squared minus x plus 2 as x approaches 2. Okay, well, what am I supposed to do here? Is it actually telling me to do something? It is. It's telling you basically, as your x values get really close to 2, what are your y values doing? That's really what it's actually saying. So you'll see that the first step in evaluating limits is simply to plug in what x value you are supposed to be approaching. That's it. In this case, we're supposed to be approaching 2, right? X is approaching 2. So don't think too hard about these things at first. It's asking, what would you expect the y value to be if x is really close to 2? So I'm hoping your response to this is, well, can I just plug in 2 for x? The answer to that is yes. You can actually literally just plug in 2 and see what happens. Now, in some problems, you end up with a sticky situation when you do that, and we will get to those. But for now, if I plug 2 in, there shouldn't be any real problem here. So if you're taking the limit of a really nice function like what we have, you can plug the x value in and you're going to get a nice y value out. And that is going to be your answer. That is your limit. So let's go ahead and do that for this one. Let me go ahead and zoom in. So x approaches 2. They're telling you, you know what? Let's just plug in 2 for x. So we'll have 2 squared minus 2 plus 2. Right? We're going to see what that is equal to. So let me simplify right below it. 2 squared is 4 minus 2 plus 2. Always do left from right. Remember order of operations. 4 minus 2 is going to be 2 plus 2. My final answer is going to be 4. So my limit here is 4. What that means is, like, if you were to graph out this function, you could graph it out on Desmos. X squared minus x plus 2. You guys can go ahead and do this if you want. Graph it out. And sure enough, if you look on your graph and you find your x value of 2, see where it hits your graph, it's going to have a y value of 4. This point, 2, 4, that is going to be on that graph. So now, remember what I said, sometimes you can get into sticky situations where you try to plug in the number and you can't. Let's pretend we couldn't. Let's pretend that I couldn't plug in 2 right off the bat. So what I want to do is I'd like to stay with this concept of getting really, really close to the value. Let's think about that. What it's telling you is, let's get really, really close to x approaching 2. What happens to my y values when my x values get really, really close to 2? Let's stay with that concept. So if I can't actually plug in 2, what else could I do? Well, if you want to know the y value you would get, all you would have to do is plug in x values that are getting very, very close to 2 and see what's going on with the y values that you get from that. That's it. So check it out. That's what I've done down here. Here I have my x, my inputs, I have my outputs. So again, I'm choosing x values. They're getting very close to 2, and I'm plugging them into my equation. What was my equation? Well, let me go ahead and write it down for us. It was x squared minus x plus 2, right? So if I plug in 1, I'm going to get 2. Plug in 1.5, you'll get 2.75. Plug in 1.9, 3.71. You come down here, plug in 1.999. You get something that's close to 4, right? 3.997001. So what do we assume here? Well, what you can kind of make an approximation of, or an assumption, is that as you are getting close to 2, your y values are getting close to 4. Okay, so if you notice this little notation down here, it says left hand limit. Why does it say that? It is important. It is a concept that we're going to talk about. What this is saying, what left hand limit means, is that you are approaching your number or let me reiterate this. You're approaching your value for x in question. You're approaching it from the left-hand side. So let me go ahead and draw a number line for us, right? We wanted to see what was happening at 2, right? What's going on here with our y values? So in this left-hand side limit, we were picking values that were slightly less than 2, and we were seeing what happens when we plug them in. A right-hand side limit is doing the opposite. Instead of choosing values that are slightly less than 2, we choose values that are slightly greater than 2. So you guys can see that over here. On this other side, I'm going to circle it. I have my right-hand limit. I start at 3, then I work my way down to 2, right? 2.5, 2.1, 2.01, 2.001, and then finally to 2. And what we can see here, let me erase this. What we can see here is that our y values are also getting close to 4. Okay, so this is a lot of work right here, obviously, right? I had to plug in 1, 2, 3, 4, 5, maybe like 10 numbers to figure out what's happening. Now, sometimes this is the best way to do it, and other times we can do what we just did before, above, right here, where we just simply plug in the number. Okay, so hopefully this makes sense. Hopefully this isn't too crazy of a concept. If it is, write down your questions. We can talk about it. So this is a good place as any to kind of reiterate this idea of a left and a right-hand side limit. So since a limit is the expected y value, right, it's what we expect y to be when x approaches a. A left-hand side limit, once again, is the expected y value when x approaches a from the left. Or when you deliberately choose x values that are slightly less than a, right? A right-hand side limit is the expected y value when x approaches a from the right. So remember my little drawing there, right? If I said that a is here, pretend that's a straight line. A is right here in the center. We want to figure out what the expected y value is when we plug a into our function, but we can't quite get to it for some weird reason. We would deliberately choose values that are to the left of a, aka smaller x values, right? And then we would do the same thing. Let's pick some right values and figure out what those are. So that's the idea of a left-hand side limit and a right-hand side limit. So you can see why the left column in the table above that we just talked about is called the left-hand side limit. The values are from the left side of the value in question A, and then the right follows with the same logic. Okay, so talking about this, there is some notation to denote if you are talking about a left-hand limit and a right-hand limit, and that is going to be down here. So check it out. It's not too crazy. Left-hand limit, if you notice, you see your familiar, well, it's not all that familiar, but we did talk about it before, your limit notation, right? I have the limit of f of x, and then down here, as x approaches a, and you guys check this out, you see this little, like, minus sign? That means it's from the left. It's from what I like to call, like, the negative, or the less than sign. When you think about minus, you think about something that's less. So, or, I'm sorry, less. So left hand limit, this is your notation. Some people like to think of this as like a little exponent here, like it's a raised to the negative. It's not really an exponent, but you can kind of think about it as being in the exponent position. But that is what denotes a left-hand side limit. A right-hand side limit is everything's the same, except if you notice, there's not a minus sign there in the exponent position above a, it is now a plus. And that means that you are approaching x, or I'm sorry, you're getting close to a from the right side. So that's what that means. That is the notation for them. You guys will see that throughout your textbook, and you're going to have to start to play around with this stuff in your homework as well. So don't be scared by the notation. It's not that crazy. You have it here. You can jot it down. So there we go. Keep in mind, it's not really an exponent, it's just notation, right? It is easy to miss or confuse these things, but once you get it down, it is not going to be too crazy. Little tip for me, the way that I like to think about it, the minus is from the side that's less, which is always left, right? And the plus is from the side that is always greater, and that's why it's plus, and that is from the right. Okay, so let's keep moving on to this other concept of, like I said before, sometimes we can't actually plug in the number that we're approaching. Why? Why is that? Well, we're going to explore it. So why don't we just plug in x is equal to a and get a y value all the time? It seems like it's the way to go, right? It seems pretty straightforward. Well, let's go ahead and take a look at an example and discuss why. So here we go with a little bit of trig. I know a lot of people don't like trigonometry, but it is what it is. Here we have an example, 2.21. Find the limit of sine of x divided by x as x approaches 0. So if you want to pause the video for a second and just kind of think about that, what would happen if you plugged in 0? Right? Well, sine of 0 is 0, right? And if you plug 0 into x in the denominator, that's just going to be 0. So I see a problem. I hope you see a problem as well. We're going to end up with 0 divided by 0. Now, what the heck is 0 divided by 0? Do you know what 0 divided by 0 is? It's undefined. I don't know what that is exactly. What we call that now is indeterminate. It is technically called an indeterminate form. So usually 0 over 0, when we get that, when we're doing these types of problems, when we're doing limits, usually when we get 0 over 0, it's telling us something weird is happening with our function. We'll talk about what type of weird it is, but you can just pause and say, oh, something weird is happening here, for sure. I don't know what it is, but it is weird. And you guys can graph it out and maybe you'll see something weird happening. So since we can't actually evaluate the function, right? We can't actually plug 0 in. We got 0 over 0, that doesn't tell us anything. What we can do instead is kind of what we did before. Take a look at what happens when we plug in numbers that are getting very close to 0. So check it out. I have it done here in this little chart. So if you notice, I have, I'm going to label these. I have left-hand side and right-hand side, right? So we're looking at 0. This side right here is the right-hand side, right? This is the right. Because if you take a look at my values here, I'm getting closer to 0, but I'm getting closer from numbers that are a little bit greater than 0, right? And then over here on the left-hand side, so I'm going to go ahead and write on the left-hand side of our screen here, this is the left. This would be the left-hand side limit. Because my x values are negative. They're on the other side of 0, right? They're on the left-hand side of 0. So it's kind of like flip-flop from what I had above, but I have the right-hand side, I have the left-hand side. Let's take a look at these numbers. You guys probably already can see what's happening here. So as we plug in, let's do the right-hand side first. 0.1, 0.01, 0.001, right? This is getting closer to 0 over here. And if you look at the y values, check out the y values. Y values look like they're getting closer to 1. So from the right-hand side, it looks like as I approach 0, let me go ahead and draw a number line here. 0 is here. As I'm getting closer to 0, as I'm plugging values in that are on the right-hand side of 0, my y values look like they're getting closer to 1. Now let's go ahead and explore the left-hand side. So similarly over here, as we choose x values that are to the left-hand side of 0, right? Negative 0.1, negative 0.01, right? So on and so forth. We get closer to 0 from the left-hand side. Our y values are also getting close to 1. So we can kind of see the same thing happening over here. So what the heck does that mean? Well, when you actually try to plug in 0, you found 0 over 0, right? When you actually try to evaluate limit by plugging in the number that x is approaching, you got something that didn't make sense. No one knows what 0 over 0 is. If you know, you got to tell me, because that would be great. But I don't know what it is. So we do this, and we figured out, okay, well, as we approached x, or as we approached 0 from the right and from the left, it looks like our y value is going to 1. So what we can say here is that this limit is actually equal to 1, which is pretty interesting. I don't know if you guys are blown away, but that's kind of cool, man. So you want to remember this. This is actually an important limit. You will see it again, so you can make a note of it or highlight it or whatever. If you guys got a note on a test, I'll let you know. but it's important to remember it does come up again. So maybe your next question to me is, and I know I can't hear you because you're watching a video, but maybe your next question is, okay, so if I can't plug in the number that I'm approaching, if I can't plug in x is equal to a, because I'll divide by 0 or something bad like that, could I just plug in x values close to a, right? Would that work for me? Well, wrong. So I'm not trying to confuse you guys, but let's go ahead and look at our next example. Because sometimes when one thing works, you don't want to make the assumption that that approach or that method is going to work for all problems. That's really what I want you to take away from this. If you can do something for one problem, it might not work for all problems, so you don't want to make the assumption. Let's go ahead and take a look at this problem. So, example 2.22. We have the limit as x approaches 0 of the square root of x squared plus 9 minus 3 divided by x squared. Okay. And what are we approaching? Well, it says x is approaching 0. So we can't actually just plug in 0. You guys can probably see why. If we do that, we will literally have division by 0. That's a problem. We actually will have 0 on the top, which is a problem as well. So we'll end up with 0 divided by 0, which new vocabulary word is called indeterminate. It's an indeterminate form. We can't determine anything about it. So let's go ahead and try the method that we just did for the last problem, right? The last problem, we said, you know what, I can't plug in 0. Let's go ahead and plug in values that are getting close to 0 from the left and from the right. So I have that here. I have that in my little chart here. So if I plug in x values, my x values are getting close to 0. So let me go ahead and fill in my chart here. This is, I'll do it in blue. So I'm getting close to 0. Let's do this side first. This is from the right, right? This is from the right-hand side. This is a right-hand side limit. I'm getting closer to 0 from values that are to the right of 0. Looks like my y values are approaching 0. Let me put a 0 there. 0.1666, and then it keeps going on. Okay, so we'll just leave that for a second. Then if we look at our left-hand side, so we'll put left over here. Again, we're choosing values that are approaching 0 from the left of it, right? Looks like our y values are going to 1.666. So, should we be done with that? Well, based off of what we've done so far, if we accept this work to be valid and to be just done, we're done with it, we would say, well, it looks like the limit of this problem is equal to 0.166 repeating. However, dun dun dun, look at this graph. So if you guys take a look at this graph, this is our function graphed out, and if you guys notice, at 0, so x is 0 here at the origin, right? Our y value would be right in here. And I'm going to erase this in a second. I just dotted it in blue. But that would be like where our y value is, right? When x is 0, there's our y value. Now, if I erase this, right, and if you just look at what I have here, it looks pretty good. They're like, well, it is what it is. However, if I zoom in, so let me go ahead and zoom out because my screen was way too blown up for you guys. Let me go ahead and, there we go. If I zoom out, if you guys have looked at the notes, this probably isn't that entertaining, but it is entertaining for me because I'm going to pretend like you guys are going through this for the first time and it's super exciting. So we've taken a look at the graph, right? What I'm going to do is I'm going to zoom in on this graph and just show you guys why we actually shouldn't accept this answer as being valid. So let's take a look. As I zoom in a little bit closer, still looks good to me. So right now, if you guys can see, the window is this. I'm really zoomed in here in regard to x and y. Really zoomed in. If I zoom in even further, however, holy crap, what happens? It kind of blows up. I'm very zoomed in here. So what you can see is that as I'm really getting close to 0, something crazy is happening. The graph is no longer going to one y value. it looks like I have some discontinuity. I have some breakups in here. So that window is extremely zoomed in. If you guys check it out right here, this is how much I'm zoomed in. I'm going to underline it in blue. So that's my window there. This looks bad, right? What the heck's going on? So apparently, if we choose x values very close to 0, extremely close to 0, how close? This close right here. We start to get some really weird y values. So what does that mean for us? Does that mean that our answer isn't what it should be? Is it not 1.66666? What's happening? Now this is going to flip you guys out. The answer is actually 0.166. The point that I wanted to make here is that if you plug in numbers close to x is equal to a, it's possible that you get something that is very, very weird. Now, the reason why this limit is going to be 0.166 is going to be something that we're going to explore later, but all that I really wanted to show you guys is that it is possible to get some really funky stuff when you zoom in on these things. So I hope you're not sufficiently frustrated yet, but if you are, that's totally okay. That's part of the fun of math. And you might be listening to me saying, you're insane. But the fact of the matter is that some really interesting things, come into play, and we're going to discover some interesting things and interesting properties. And the thing to do is to not get super frustrated, because you guys can do this. It is just a math course, and it is fun when you kind of just take a deep breath and realize that this has been done before, and you will be able to do this, and you will get through Calc 1. It is not a problem. So, going back to this problem, what we're seeing is that if you just simply plug in x values that are close to a, it may lead to a problem. It might be fine. Or it could be weird. But we always need other ways to be able to calculate limits. So I'm kind of jumping ahead, as what we're going to do in the next section kind of deals with this a little bit further. But at this point, just know that we have methods to take care of these pesky problems. We will. For now, though, let me keep moving on in these notes. And before moving on to some of the really cool limit methods that we have, let's go ahead and look at some limits visually. So we did it algebraically before, where we saw what the limit was, and we literally plugged in what x was approaching, right? In our first problem, we plugged in 2, figured out it was 4. In our other problem, we couldn't quite plug it in, but then we said, okay, well, let's just choose values that are getting very close to our value in question and see what happens. This is now going to be a visual problem. So, okay, here we go. Example 2.23. Consider the following graph. So hopefully you guys can see this over on the right hand side of the screen. We have a graph there for ourselves. What we want to do is utilize that so that we can answer our questions. So let's start off with question 1. It says the limit of f of x as x approaches -1 from the left is equal to what? So let's go over to our graph here, and I'm just going to write this in red. So let's find -1 first. I'll just make a dot here on -1. -1 is right here in red. There it is. And we want to look at, what happens with my y values as x gets close to -1 from the left. Okay, as x gets close to -1 from the left. So as you're coming in to -1 from the left-hand side, where is your y values going? Well, what I see happening is they are, let me erase this and write this a little bit more clearly. Let me zoom in here for a second. So what it's saying is, as I'm getting closer to -1 from the left-hand side, where are my y values going? So what I see is they are going here. So there's your y value. As you get close to -1 from the left, your y values are going up to +1 on the y-axis. So I would go ahead and say the answer to that would be +1. Okay, so let's go ahead and move on to the next problem. So the next problem, number 2, says the limit of f of x as x approaches -1 from the right. So let me go ahead and zoom in. Let's talk about this one in blue. Here's -1. We had it marked in red, and we are approaching -1 now from the right hand side. Where are my y values? Well, if I was looking at this value, this is down here, getting closer, this is down here, getting closer, this is down here. If I get close to 1, it looks like my y values are now down here. And if I zoom out for a second, that looks like -2 on my y-axis. Okay, so hopefully that makes sense. So once again, the expected y value there would be -2 when we approach -1 from the right. Okay, so let me go ahead and fill that in. This is -2. All right, cool beans. Number 3, the limit of f of x as x approaches -1. Oh, interesting. If you guys notice, number 1, right? Number 1, it was approaching from the left. Number 2, it was approaching from the right, right? Number 3, it doesn't look like it's approaching from either side. It's just there's no notation, right? There's no notation for a left-hand side limit or a right-hand side limit. So what's going on? What we call this is a general limit. If you're approaching from the left-hand side, it's a left-hand side limit. If you're approaching from the right-hand side, it's a right-hand side limit. If you just have the limit of f of x as x approaches some number in general, this is called a general limit. Now, a general limit exists when its left-hand and right-hand limits are going to the same y value. So this is very important. This is a very important concept. Look at what happened with our, I'm going to put a star next to them. Look what happened with our left-hand side limit. It was going to 1. Look what happened with our right-hand side limit. It was going to -2. Because the left-hand side and the right-hand side are going to 2 different places, we would say that the general limit does not exist. So I'm going to put D and E for does not exist. So just to reiterate this, this is because the left-hand side limit does not equal the right-hand side limit. When they are not equal, the general limit does not exist. Very, very important concept, easy to forget, but also easy to remember and easy points on a test. So let's keep moving on with our problem and see what else we got. So I kind of make a note of that. Let's do 4 first before I read that blurb. So number 4 says, find the limit as x approaches 1, as x approaches +1. So keep in mind here, this is a general limit. We are not looking at the left-hand side of +1 or the right-hand side of +1 separately. We're looking at it all together. So let me go back up to my graph. Let's identify where +1 is. Let me go back up here. Let me erase some of this other stuff that was about number 1 through 3. And let's go to where number 1 is. Let's write this in green. So number 1 is right here, right? And as we approach, now when you're looking at a general limit, what you want to do simultaneously is look at what's happening to the left and from the right. So from the left-hand side and the right-hand side, they both seem to be going to the same place. And so I would go ahead and say that the limit as x approaches +1 in general is 2. Why 2? Well, because that's where it hits my y-axis. So hopefully that makes sense. So now I'm going to go ahead and read that blurb. So let me go back down here. This is pertaining to this question. So note, this is not a one-sided limit. This is a general limit. A general limit only exists if the left and the right-hand side limits equal the same. So if they're going to the same number, the same y value. So what did we say here? This was going to be equal to 2. Cool. So there it is. Okay, let's talk about number 5 now. So number 5, we have another general limit. If you guys can take a look at that, it says find the limit of f of x as x approaches positive 2. So if we go back up to our graph here, we're looking at positive 2. So at positive 2, let's do this in red. So if we look at positive 2, again, this is a general limit. So what you want to do simultaneously is look to see if your left-hand side and your right-hand side are going to be coming into the same y value. So if we look at the left-hand side first, so remember this is 2. So if we look at what's going on when we approach 2 from the left, looks like our y values are coming down, right? They come down to this, kind of like this empty circle, right? This hollow circle here. If we look at the right-hand side, it looks like our y values are going to the same place. So it's consistent with this idea of my left-hand side and my right-hand side going to the same y value. So if I go back down here to my answer, I'm going to go ahead and say that this general limit does exist. And because the left-hand side and the right-hand side were both going to the same thing, we can go ahead and say that this is going to be equal to 1. Let me go back up there and verify that. I didn't actually say that when I was writing it out, but let's reiterate this, right? Left-hand side, right-hand side, they're going to the same thing, and this y value here is positive 1. So there we are. Okie dokie. I don't know if I have another one. Yep, yes I do. Number 6, here we go, and number 7 and number 8. So we have 3 more to do. Here we have the graph to the right-hand side of the screen. Let's go ahead and take care of these. So number 6 says, find the limit of f of x as x approaches negative 2 from the left. So if we're looking at negative 2 from the left-hand side, first of all, negative 2 is right here. I'm just going to mark it in red. And if we're looking from the left-hand side, we're looking at things that are less than 2. So if it's coming in this way, where does my y values seem to be going? Well, if you guys can see, what does that look like there? What I see is something that we learned in algebra, which is called a vertical asymptote. I see that there's like a split here, right? And that is consistent. If you guys were thinking, oh, that looks like a vertical asymptote, you're completely correct. Mm-hmm. It is. So what are we going to put for our answer here? Well, what happens to our y values as we get close to negative 2 from the left-hand side? What do you guys see happening? Well, my graph seems to be shooting up to positive infinity. So maybe your assumption would say, well, maybe I should write that my answer there for that limit would be positive infinity. And to that, I would say you are correct. Nice. Yes, that is exactly what we're going to write, because that's exactly where our y values seem to be going. Let's go ahead and move on to number 7. The limit of f of x as x approaches negative 2 from the right. Okay, so I'm going to do this in red. Again, we're looking at this way. We're looking at what happens when we get close to negative 2 from the right. And your answer hopefully would be, well, it looks like my graph is shooting down to negative infinity. So I'm going to go ahead and say that this is negative infinity. All right, number 8. So remember what we said before about general limits. Number 8 says find the limit of f of x as x approaches negative 2 in general, right? So number 6 and number 7, we were talking about negative 2 from the left, negative 2 from the right. So what can we conclude about number 8? Well, hopefully you're sitting there saying it doesn't exist. Why is that? Well, the reason why this does not exist is, remember, the left-hand side limit has to be equal to the right-hand side limit. So the limit as x approaches negative 2 from the left of f of x does not equal the limit as x approaches, as x approaches negative 2 from the right. So because they're not equal, we would say that the general limit doesn't exist. So your next question might be, oh, okay, Eileen, so what if both of the left-hand side and the right-hand side are both going to positive infinity? Would the limit exist? Yeah, the limit would. You can have something go to positive infinity, and that's okay. It really just matters about the left-hand side and the right-hand side limit going to the same thing. If they go to the same thing, you are good to go. Your general limit exists, and it is whatever your left-hand side and right-hand side are going to. Okay, so let's keep moving on here. Example 2.24, consider the following piecewise function. Okay, so we talked about piecewise functions in the, I guess like the chapter 1 review. So we're going to be talking about them again, except we're going to be using limits to define and understand our piecewise function. So here in our piecewise function, we have 3 domains, and we have the formulas, if you will, that are defined by those domains. So let's go ahead and answer part 1 here. Part 1 says, what is the limit of f of x as x approaches -1 from the right? So first and foremost, once again, we're dealing with a right-hand side limit. We don't have to graph this to look at it. You really don't have to. But what we do have here is a function, and that's why we don't have to graph it. We have the function. We have the piecewise function in front of us. So let's utilize that. So since this is a right-hand side limit, it means that we're going to be using x values slightly larger than -1, right? That's where we would be looking. So what we want to do is go to our domains and figure out where that fits in. Okay, so I'm going to go bottom to top. So if we're choosing values that are a little bit greater than -1, this domain, this bottom domain, would not work. The x values that are in that domain are greater than 2. Okay, totally not that one. That doesn't work. Let's go to the next one. This one here. So this domain is including all numbers that are a little bit greater than or equal to -1 and less than 2. I would say that that probably works for us. Just to be thorough, let's make sure that this top domain doesn't work. All the x values here have to be less than -1, and from what we are looking at, remember, we're trying to choose values that are getting close to -1 from the right. So it's consistent. This middle domain is the domain that we are going to be looking at. That means that what I'm going to do is I'm going to literally plug in -1 into that formula and see what happens. So if I plug in -1, right, what we are going to do here, I'm just going to rewrite this. We would have the limit as x approaches -1 from the right, and we're going to be plugging it into -x, right? That's where our numbers fit into our domain, so that's the formula that we're using. If we do that, if we plug in -1, we would have negative on the outside, then -1, negative, negative, make a positive. So this would be +1. And that would be our answer there. Okay, let's go ahead and move on to the second problem here. So the second problem is another, what do we got here? We got a left-hand side limit, right? So we want to look at what happens when we approach -1 from the left-hand side. So what does that mean? Well, that means we have to go to our domains. We have to figure out where this fits in. So left-hand side means we're going to be plugging numbers that are slightly less than -1. So what that means for me is probably this one right here. Okay, so that means we're going to utilize that part of our function. So the limit as x approaches -1 from the left, we're going to plug that into x squared. If we actually evaluate this, it's going to be -1 squared, and this is going to be +1. Okay, so now when we're coming down to part 3, notice that part 3 is the general limit of what we just did, right? We first looked at, in number 1, the limit as x approaches -1 from the right. Then part 2, the limit as x approaches -1 from the left. And now we have the general limit, the limit of f of x as x approaches -1 in general, right? So what do we got? Well, the left-hand side and the right-hand side match, so they're consistent. And what we can say here is that 3 is going to be equal to 1. And that's it. Remember, general limit. All you really have to ask yourself, does the left and right hand limits equal each other? If they do, boom, you're done. That is what your general limit is also equal to. Okay, let's move on to part 4. Now, part 4 is just this by itself. It's the limit of f of x as x approaches 2 in general. Now, this is a general limit, and we haven't really computed the left and right hand side limits for this yet. So what we have to do is actually break it down. So this all here, this is like extra writing that you wouldn't normally have on a problem. What you would have is just what I underlined. You would only have the limit as x approaches 2. You would have that. What you would have to do then, you would say, oh crap, I need to see if what's going on with my left-hand side and my right-hand side. And then you would have to break it down into what I circled. So let's go ahead and discuss this. We want to look at the limit of f of x as x approaches 2 from the left first. So let's do that. What that means is we'd be choosing numbers that are slightly less than 2. And I think I don't have my function, so let me go ahead and go back up here. We want to circle which one this pertains to. So things that are less than 2, let's circle this in blue. I think that's going to be this one here, right? It's going to be that one there. Greater than 2 would be this one. So I pointed to it. So the left-hand side limit, we're going to use this. We're going to say, for this one, it's going to be the limit as x approaches 2 from the left. And we would be plugging that into negative x, right? So if we do that, we're just going to get negative 2. That's our answer for the left-hand side limit. Right-hand side limit, I pointed to the function that we had. I'm just going to go ahead and jot it down for us. What it was limit as x approaches 2 from the right. Oh, actually, let me go back up. What did I point to? I pointed to square root of x minus 2. So let me go ahead and write that down. It's going to be square root of x minus 2. If we plug 2 into that, we're going to get the square root of 2 minus 2, which is equal to the square root of 0, which is just 0. Okay, so now we know what the left-hand side is and the right-hand side. So let me go ahead and make a summarization of this. The limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x. How do I know that? Well, I know that because we just did it. Check it out. Left-hand side limit was equal to negative 2. Right-hand side limit was equal to 0. That tells me that my general limit does not exist. So we'll go ahead and say, so the limit as x approaches 2 in general of f of x does not exist. DNE for does not exist. And there we are. Okay, let's keep moving on. Let's see, what do we got? A couple more types of problems that are interesting for us. So, example 2.25. The limit as x approaches 1 from the left, or I kind of read that backwards. Let me reread that. So find the limit of 5 plus x divided by x minus 1 as x approaches 1 from the left. All right. And do the same thing as x approaches 1 from the right. So it looks like we have a left-hand side limit and we have a right-hand side limit of the same thing. So if you guys notice, when you plug in 1 in the bottom of both of those fractions, you will get 0. So you'll learn in a little bit that when you plug in an x value and you get 0 divided by 0, it means that you have a little bit more work to do. These methods we'll learn in a little bit later. If you plug in an x value and get a non-zero over 0, like let's say you get 5 over 0 or negative 3 over 0, what it means is that your final answer, and you're going to have to do a little bit of work to get here, but your final answer is going to be either negative infinity, 0, or does not exist. You have those three options. So once again, when you have some finite number over 0, like 2 over 0, or 3 over 0, or 6 over 0, just by evaluating your limit, you will have 3 possible outcomes: negative infinity, positive infinity, or does not exist. Now, what you would need to do then is figure out which of the 3 outcomes your problem is equal to. So let's go ahead and discuss this. Number 1 here, we're going to do this with this problem. If we have the limit as x approaches 1 from the left, if you guys notice, if you plug in 1 in the denominator, we're going to have division by 0, right? If you plug in 1 up top, you're going to get 6. So your answer here, I have it typed up for us, is going to be 6 divided by 0. So what's the limit? Well, the limit is going to either be equal to negative infinity, infinity, or does not exist. So For this problem, it won't be does not exist, and I'm going to show you guys why. Now, it's possible that it can, but when you have a one-sided limit and something like 6 divided by 0 comes out when you plug in your values, it's either going to be negative infinity or positive infinity. Why? Well, because you have a one-sided limit. So your one-sided limits are always going to be negative infinity or positive infinity. You're never going to get a does not exist here. When you take a general limit, however, it's possible to get DNE or does not exist. But for now, for this left-hand side limit, when we get the case of 6 divided by 0, it's going to be either negative infinity or infinity. We just got to figure out which one. So the easiest way to do this is to check the sign of the top and the bottom, or the sign of the denominator and the numerator, or whichever way you want to think about it. What we want to do is choose an x value that's very, very close to 1. Why 1? Well, because remember, that's what we're looking at. We're looking at what's happening when x approaches 1, specifically from the left, right? Okay, so here we go. I'm going to zoom in here. If you chose something that was really, really close to 1 from the left, it would be less than 1, would it not? Hopefully you're saying yes, right? If you look at your number line, and 1 is right here, here's 1. If you choose something that is less than it, that is just from the left-hand side, it's going to be less than 1, right? It's going to be like 0.9. Let's go with 0.9. Okay, let's say I plugged in 0.9 up here. So I'd have 5 plus 0.9. That outcome is always going to be positive, is it not? Hopefully you're saying yes. In the bottom, if I plug in 0.9, I would have 0.9 minus 1. That outcome is always going to be negative, is it not? Hopefully you're saying yes. So what we end up with here is positive. We end up with a positive number divided by a negative number. Now remember, what is a positive number divided by a negative number? It's always going to be a negative number, right? The answer is always going to be negative. So remember, I told you, the possible outcomes here are either positive infinity or negative infinity. We got a negative outcome, so the answer here is negative infinity. It's kind of like a little bit of a shortcut here. So if I zoom out, you guys can see that's my answer there. So the ratio, right, the division there is going to come out to be negative. Positive divided by negative is negative. Therefore, it's going to be negative infinity. Okay, so it's probably a lot to digest. Let's go ahead and work through another iteration of this. Let's say we wanted to do the same thing for this here. We wanted to figure out, okay, I know that when I plug in 1, I'm going to get, let me just do this again for you guys. I'm going to get 6 divided by 0. So the outcome here is either positive infinity or negative infinity. I have to figure out which one it is. We have just done this for the left-hand side. Now we want to do it for the right-hand side, right? So I'm going to erase this here, and we're going to do what we just did. We're going to think about what's happening with the positive and negatives. What's going on here? So if I do my number line, here's positive 1. And I'm choosing numbers that are from the right of it, that are a little bit greater. So let's say we did 1.1. Okay. If I plug in like 5 plus 1.1 divided by 1.1 minus 1, the outcome on top is going to be positive, divided by the outcome on the bottom, which is also positive. Now remember here what I told you guys. When you have this case, what was our case? We had 6 divided by 0, right? That's technically undefined. So when you have this case, you are either going to have positive infinity or negative infinity. You got to figure out which one it is. We did our number, or our sign analysis, if you will, just now. And we got positive divided by positive, which gives you a positive outcome, which means this is a positive infinity. And there you have it. There's your answer. So I kind of have this typed up for us down here. And it's consistent. So left-hand side limit is negative infinity. Right-hand side limit of this problem is positive infinity. And there we are. Now, if you were to go on and ask what the general limit is, which I have here in step 3, I have this typed out for us, and I'm going to write it. We would say, hopefully you guys can see this, the general limit here, hopefully you're saying this to yourself, it wouldn't exist. Why wouldn't it exist? Well, The left-hand side was going to one place, the right-hand side place was going to a different place. They are not equal to each other, and therefore the general limit does not exist. Okay, so let's keep moving on. Again, remember these notes are on D2L. They're typed up for you with all the solutions. If you guys need to look at them instead of my lecture videos, you are welcome to. Let's go ahead and take a look at this example here. Let me go ahead and zoom in. So it says example 2.26, find the limit as x approaches -5. Notice that this is in general, right? It's not a left-hand side or a right-hand side, it's just in general. Okay, so find the limit as x approaches -5. That's where we're looking. And we are looking at this function x minus 1 divided by 5 plus x, and then the whole thing squared. There it is. So you almost always want to start by just simply plugging in the number that you're approaching and see what happens, right? See if you can do it. So I've kind of done it here. I've typed it up for us. So if you do this, if you plug in -5, let's see what happens. If I plug in -5 up top, I'm going to end up getting, let's see, -6. And then on the bottom, if I plug in -5, I'd end up getting, what, 5 plus 25. So I'd end up getting -6 divided by 30. And that seems to be an acceptable answer. Right? I would end up getting -6 divided by 30, which actually comes out to be -5. So that seems to be my answer there. Let's go ahead and look at a left-hand side limit. So if I look at a left-hand side limit, remember that we would be choosing values that are slightly less than -5. So I think there's a typo here, and I think I want to change this for a second, because right now it's not a problem that really presents us with the need to do a left-hand and right-hand side limit. So let me go ahead and change this just a little bit. Oh, you know why it's like this? It's because there's a typo here, and I just didn't even see it. So typo, somehow I've changed my original problem from what's written down here. So that's my bad. Let me fix that, guys. So it's supposed to be the whole thing squared, right? So this is not the correct denominator down here. You guys probably saw that, but I can't hear you say anything, so I just keep going until I figure out that I've made a mistake. Okay, so what this should be, it should actually be -5 minus 1 up top, and then on the bottom it should be 5, and then it's going to be -5, and the whole thing squared. So really this is going to be -6 over 0. Okay, there we go. There is the type of problem that we've just been looking at. Now this makes sense. Now you guys can see, okay, this is weird, right? We have -6 divided by 0. That tells me that the answer to this general limit is either going to be positive infinity, negative infinity, or it does not exist. Okay, we got to figure out which one it is. In order to do that, we need to break this down into a left-hand side limit and a right-hand side limit. Let's do the left-hand side first. That's what I have typed up down here. So the left-hand side limit, we're going to look at what happens when I approach -5 from the left. So if you think about this in terms of a number line, here's -5. We're looking at values that are less than it. So if you need a number, let's say, I don't know. Let's say we chose like -6. Yeah, why not? -6. Let's do that for now. It's kind of far away from -5, but we want to think about it as being that. Okay, so if you chose -6, if we plug -6 into the numerator, right, you would get like -6 minus 1, and that would be a negative outcome, right? In the denominator, you would have 5 plus a -6 squared. Okay, well, no matter what's going on in the bottom, you're always going to square it, so it's always going to be a positive outcome. So really what we have here is negative divided by positive, which means we have a negative infinity here. Remember, when you ever have a finite number divided by 0, your outcome is either negative infinity, positive infinity, or it doesn't exist. So now we've taken steps to figure out which of the three it is for this one, and it's negative infinity. Now let's do a right-hand side limit. So we want to do the same thing, choose something from the right-hand side of negative 5. So we'd be coming in this way, and you guys could choose maybe negative 4. How about that? So if I plug negative 4 in, that means I'd have negative 4 minus 1. The outcome on top is always going to be negative. And then on the bottom here, if we chose negative 4, 5, yikes, can't talk, 5 plus a negative 4, we are always going to square this. So once again, the outcome here on the bottom is going to be what? Is going to be positive probably, right? So positive divided by negative is negative infinity. So we ended up with negative infinity again. Hopefully that makes sense. Okay, so what we can see here is that the left-hand side limit is equal to negative infinity. The right-hand side limit is equal to negative infinity. So the general limit, let me go ahead and conclude this. So the limit as x approaches negative 5 in general of our problem, I'm just going to write it all out, is equal to negative infinity. Remember what I told you guys, infinity is an okay answer. It's fine. Your left-hand side and your right-hand side have to be going to the same place. It doesn't matter where it is going, as long as it's the same place, that's what your general limit is going to be equal to. Okay, guys, we are almost done. Let's talk about something else. So here we have our last example, I think, for the day, if I can remember. Maybe not. Maybe I have a little bit more for us. I might. I don't remember. But let's go ahead and do this one. So we have the example 2.27. Find the limit as x approaches 0 of sine of pi divided by x. So I think for this problem, looking at the graph could shed a little light on what's happening. If I graph this out, and you guys are welcome to graph this out on Desmos, as you look at what's happening as x approaches 0, you guys can see that this is oscillating. So something kind of strange is happening. If I wanted to zoom in a little bit more, it even gets a little bit more crazy. It doesn't really even seem to help to zoom in. It seems to get a little bit more sporadic. If I zoom in even further, it gets even worse. So it actually seems like it's getting more chaotic the more I zoom in. And in fact, that's exactly what's going on. In this case, the limit does not exist. If you're thinking about Mean Girls, I am too. That's from that movie. Hopefully you guys know what I'm talking about. Otherwise, it's really awkward. But the limit does not exist here because it will never actually approach one point. Remember, in order for a general limit to exist, it has to approach from the left and from the right. It has to approach the same number. And in this case, it's continually oscillating. And if you know anything about sine and cosine, you guys know that they do oscillate. Sometimes when you do some things to a sine function or cosine function, you can really change the way that it looks. And you can make the oscillations a little bit more crazy. In this case, it's kind of what we see here. And so what we can conclude is that the limit doesn't exist. But let's try to approach this in a slightly different way. So let's just take a look at pi divided by x. All right, so as x approaches 0 from the right of pi divided by x, this is going to go to infinity. Okay, so what happens to the sine function when the inside goes to infinity? Well, remember, it's always oscillating between -1 and 1. That's what it does forever. Well, that's exactly what is happening when you take the limit as x approaches 0 of sine of pi divided by x. So as x goes to 0, the sine function keeps oscillating between -1 and 1, and it never approaches one specific y value, no matter how close we get to 0. Therefore, therefore the limit as x approaches 0 of sine of pi divided by x does not exist. So, let's go ahead and move on to another example. So if this was kind of confusing, don't worry, we are going to approach this process in a little bit different way with another technique or another method of limits. It's called the squeeze theorem. But for now, we're going to keep moving on. You guys can reread this and explore this if you'd like. I'm going to keep moving on to what I think is my last example. Example 2.28. Sketch a graph that satisfies all of the following conditions. So we have 6 conditions there, and we want to be able to successfully graph these things. Sometimes this is a really challenging problem for students because they're taking their information and they're interpreting it into a graph. So I like to go step by step. If you guys notice, there's already two dots on the graph right there. Those are actually 2 things that I've already plotted for us. So let's go ahead and get into this one. Let's start with number 1 first. So let me go ahead and I'll just do this in red, I guess. Number 1 here, the limit as x approaches 0 of f of x, or let me reread that. I always read these backwards. The limit of f of x as x approaches 0 is 1. So one thing to make a note of is that this is a general limit, right? It's a general limit. That means that what we can assume here is that when we approach 0 from the left and from the right, the y values are both supposed to be going to 1. So let's go ahead and write that up here. I'm going to make this right here and like do these little lines to the side. That means that from the left and from the right, they're both going into that same value. Now, if you notice, I've left this hollow for now because I don't really know if that point actually exists there. It could be hollow, it could be solid. I'm not sure for certain. Okay. Because this is just a limit. What that means is it's approaching from the left and from the right, it's approaching the same thing. Now, whether or not that dot is solid is something else we're going to talk about later. For now, let's move on to step 2. So 2 says the limit of f of x as x approaches 3 from the left is equal to negative 2. So if we go to positive 3, and we look at negative 2, we should get some little dot down here, and we should signify that it's supposed to be approaching it from the left, right? So at 3, negative 2, that's like right here, right? We're going to say this comes in from the left-hand side. And there's its little tail. That's it. Okay, 3, the limit as x approaches positive 3 from the right is also, well, no, it's not also equal to negative 2. It's equal to positive 2. Okay, so that's telling me that if I go to positive 3 for x, I should have positive 2 from the right. So it's going to be this hollow circle and a tail from the right. And there's that. Okay, let's go to 4. The limit as x approaches negative 2 in general. Okay, so in general, that means from the left-hand side and the right-hand side, they're going to be going to the same place. Where is that place? Well, it is negative infinity. So, let's go ahead and go to negative 2. I'm going to do this in blue. I'm going to put a little bit of a line here for a vertical asymptote. And what we're going to see here is that as we approach negative 2 from the left and from the right, so let's do from the left-hand side at first, our y values are going to shoot down to negative infinity, and from the right-hand side are going to shoot down to negative infinity as well. So there's number 4 done for us. Number 5, f evaluated at 0 is equal to negative 1. So this is the point that's already plotted for us. At 0, we have negative 1. I'm just going to mark it in red for us. There it is. And then last but not least, we have number 6. F evaluated at positive 3 is equal to 1. There it is. We had that point already plotted for us as well. So there's our graph. You guys don't have to fill these in perfectly. You could connect your dots if you wanted to. Like, let's say I wanted to try and connect these a little bit better. I could do that, and I could say, you know what, this thing's going down, So I'm going to make this look a little bit nicer. Vertical asymptote still here. I could say, well, maybe this connects here, and then like maybe this comes down and connects, and then that would be pretty much it. But if you guys are worried about doing this on like a quiz or something, you do not have to be exact or perfect about it. What you do have to tell me is the direction in which these things are coming. So if you're approaching from the left, you should have like a little tail end coming into the left, or if you're approaching from the right, you should have a little tail end coming from the right. But that is pretty much it. So if you have questions anywhere along this lecture, make sure you write them down, and